waves and sound. So as we look at waves and sound, there are a few properties that we have to take a look at first when we talk about a basic wave. We talk about amplitude, and if we're talking about the amplitude relative to a rest position, this would be our amplitude. We could also take a look at how long a wavelength is, and we define a wavelength as being between the distance between two identical points on a wave. So we could talk about this as being a wave, but we could also talk about the distance between two peaks being a wavelength, or the distance between two troughs being a wavelength. In terms of half wavelengths, we could talk about the length from side to side of a peak, or we could talk about the length from side to side of a trough, or we could even talk about the distance between a peak and a trough. And if you take a look at that, you can take a ruler if you wanted to, right up to your screen, and you can measure that distance there and that distance there are the same distance. Anyway, it's half of a wavelength. A quarter of a wavelength ends up being an important measurement as well. And so half of a trough or half of a peak could be ways to measure a quarter of a wavelength. We talked about transverse wave, which is what this is a picture of. And we talked about what a frequency was. Frequency is 1 over the period, or the inverse of the reciprocal of the amount of time it takes for one wave to be formed. And units of hertz are what's usually used for frequency, but really a unit of a hertz is 1 over seconds, or cycles per second, where the word cycle isn't really a unit, so the units really are just per second. And in terms of the universal wave equation, we wrote V equals lambda F, where lambda is the wavelength we talked about over here, and frequency is the number of cycles that happen per second, universal wave equation. We also talked about longitudinal waves. And so these longitudinal waves, these waves that have compression regions and rarefaction regions, were another kind of wave. In fact, this is an example of a slinky having compressions and rarefactions, low density, high density regions. And a longitudinal wave is really what a sound wave is. Although we could take our longitudinal wave, this wave that has compressions and rarefactions, and we could graph it in terms of like the relative density or the pressure of the regions. So high pressure, high density regions, low density regions, high density regions, and low, high, low, hello. It's like it's waving to me, right? And you can see that what we're really doing here is mapping out the high density regions, these compressions, and the low density regions, these rarefactions, against our diagram. And so yeah, we could represent a longitudinal wave in a graphing kind of way as a transverse wave. And then we also talked about the temperature dependency of the speed of sound, and experimentally determined 332 meters per second plus a coefficient of 0.59 meters per second degrees Celsius times the temperature in degrees Celsius. Now you may see different places, instead of having a coefficient of 0.59, you might see a coefficient of 0.6. There's a little bit of variation on this, and it could be because of the way that these values were gathered, what altitude it was gathered at, what the relative humidity is. It's an experimentally determined value, but this is a good approximation. And if you use this equation with textbook work, it's going to work out pretty well for you. But remember, this is an experimentally determined equation, and so you do see a few different coefficients pop up depending on where you source out the equation. We also talked about Mach numbers, and just a reminder that Mach number is really just a ratio. It's a fraction of how fast an object goes compared to the speed of sound. And so anytime you have a Mach number that's greater than 1, you're traveling supersonic, faster than the speed of sound. Of course, a sonic boom only happens when you pass through Mach 1. It doesn't happen again when you get to Mach 2. I'm going to jump over to the other side of the page here, talk about this idea of Doppler effect. And I didn't write the word Doppler effect here, but we know that if we sit stationary relative to a stationary noisemaker, we're going to hear a constant frequency if that noisemaker produces a constant frequency. So if it's playing 2000 hertz, we're going to hear 2000 hertz whether we stand over here or stand over here. And it's this idea of concentric sound ripples. We talked about a model of a ripple tank or a rippling water But we talked about this being really three-dimensional spherical sound ripples rippling out from a source. And this is a stationary source. But if the source was in motion, then we know that as the source makes sound, it continues to move, and each time it, cycles through its wave production, it will have moved to a new location by the next time the next cycle begins. And so if you travel to the right in this situation, we would talk about wavelengths being shorter along the direction of travel, so that as we travel towards a listener, they would hear a higher frequency as a result of those compressed wavelengths, and the person that you're moving away from would hear a lower frequency because the wavelengths get more spaced out. Remember, since V is equal to lambda F, if the speed of sound stays the same, this wavelength, if the wavelength gets longer, the frequency decreases. And likewise, speed equals lambda F. So if the wavelengths are getting shorter, the frequency is increasing. So this person over here is experiencing decreased frequency because of the longer wavelengths, and this person over here is experiencing higher frequency as a result of the compressed wavelengths, and looks like they're running to get out of the way there. Now, if we just jump down here a little bit, just a reminder about superposition of waves. When we're talking about superposition of waves, I'm just showing the simple case of the idea of a square wave and a triangular trough coming towards each other. And when this square peak and triangular trough meet with one another, I could draw it out, and maybe I could draw it with a pencil. Square, triangle, and remember, if we take vertical slices of this and go back to the notes for details, what's going to happen is these two waveforms add up to take on a shape something like this. And for details, go back to the notes on this, but that would be the resultant waveform of those two waves being completely superimposed on top of each other. Superposition is the concept, and you want to go back and look at the details of superposition. Superposition also is what gives rise to the concept of beats. And when we have two different frequencies, one with a different wavelength than the other, and we superimpose these guys, they experience beat superposition, you may end up having a waveform that looks like this, where the blue represents the resulting waveform, and this pink envelope that I've drawn over top of it would be the beat envelope. This sort of envelope function would talk about what the frequency is of this beat. So you hear sort of a wom, wom, wom sound as these two frequencies interact with one another. And the beat frequency is the absolute value of the difference between the two frequencies. Now, we also talked about the fact that intensity drops off as an inverse square. We saw inverse square, we talk about gravity, but we also see inverse square when we talk about intensity of sound dropping off. And we start off with a sound source, and this sound source puts out a certain amount of power, fine. And as the listener gets further and further away, position R1, R2, R3, we drew sort of a one-point vanishing diagram that reminded us of elementary school art maybe. But the idea is that we have this shape that emerges from this vanishing way of drawing things that lets us see how this projected sound has an intensity that drops off. Because what we notice is, as you get further and further away, that sound energy has to spread out over an ever-increasing area. And by the time we get from 1 unit distance away to 2 unit distance away, you notice that we've spread out. If this is 1 unit of area, we spread out over 4 units of area. And as we get 3 unit distances away, I've gone away from the sound source, an equal distance each time spread out over 9 units of area. And so what we're saying here is that there's a relationship here where if this is 1 unit, this is 2 units, and this is 3 units of distance away. Notice 1 squared is 1, 2 squared is 4, 3 squared is 9. We have an inverse square drop-off of energy intensity. This energy is spreading out over an ever-increasing area. So if we take that idea and we say, well, how about we think of this really as those spherical ripples of sound energy that we talked about before. We talked about, remember, water ripples as a model, but really these sound ripples are going out spherically in all directions. Things to remember is that intensity is a measure of how much watts there are per meter squared around this surface, this spherical ripple. Remember, the surface area for a sphere, since we're talking about spherical sound ripples, is 4 pi r squared. So we're talking about the intensity of sound at position R1 being the power spread over the surface area of the sphere that has a radius of R1. Now, by the time that sound ripple has rippled out to, I'll draw this in here, sort of pre-sketched out my radius with dots. Oops. By the time that ripple gets out to a sphere that's this big, try and give it like a feeling of three-dimensionality. There we go. This same power is spread out over an even larger surface area, and we would say that the intensity 2 would be the original power at the source divided by 4 pi r2 squared, where r2 is obviously bigger, so it's being spread out even more. Now, if we take these two intensities and we produce a ratio, we can say, hey, listen, I1 over I2 would be P over 4 pi R1 squared divided by P over 4 pi R2 squared. And we could show our work, and you can go back to the notes to figure out how this all sort of shuffles out. But I1 over I2 is equal to R2 squared over R1 squared. So this intensity distance ratio is something that comes out of this conversation. And this allows us to, since distances are easy to measure, intensities may be a little bit harder to measure, we can predict what an intensity of sound is going to be at a certain distance away from a source if we know what the intensity is at a given distance away from the source. We talked about decibels, and decibels feeds into this idea of intensities as well. Remember, decibels is a way to compare intensities, and most commonly we talk about comparing an intensity, call it I1 here, to this sort of human-centric, let's just call it a human-centric standard of comparison, where I naught is equal to 1.0 times 10 to the power of negative 12 watts per meter squared, which is thought of as the quietest sound that the average person can hear. So whenever we're calculating a standard decibel, we're comparing the difference between I1, whatever intensity we're actually hearing or observing, and I naught, which is this quietest sound. Remember, since the units of intensity 1 and intensity 2 are both watts per meter squared, they're going to cancel each other out, and there's not really any other part of this equation that brings in units. So decibels, strictly speaking, are unitless, but sometimes frequently people will write it as like 10 decibels, for example, or 110 decibels. And really, they're just writing that decibel onto the end there to let the reader know what they're talking about, what that coefficient means. We're talking about a comparison of two intensities, an intensity compared to that quietest sound. Standing waves, right. So the first way that we got introduced to standing waves was the idea of resonance on strings. And so this here is a diagram, a loop diagram of a fixed-ended string. And all I mean by that is that it's fixed at both ends so that it can't vibrate at both ends. Remember, we also said that there's this slang, this jargon, where a loop, and I'll just highlight it, this is a loop. One loop is equal to half of a wavelength, which I think you probably sort of already knew, but it's nice to sort of to highlight it. Remember that the dotted line here represents the extreme position that the string could be in at one point in time, and then the solid line represents another extreme position. So this is a snapshot, but it's kind of meant to represent an animation, right? So this is a still frame of an animation, and we're getting a still frame of it in one extreme position, and then in the dotted line in pink here is the other extreme position. In terms of vocabulary, the antinodes are where the maximum disturbance is happening. The nodes is where zero disturbance is happening. So we have these antinodes and nodes. I'll write the word out. Antinode. And node is spelled the same way, but without the anti. Let's just say that we have a string that's 10 meters long and it has 4 loops on it. So if I take a look at this and I say, well, one loop is half a wavelength, and we say the string is 10 meters long, I'm going to slide sideways here and say that if there are 4 loops and each loop is half a wavelength long, then 4 half wavelengths is equal to 10 meters. And so I could use this process. You can follow through the simplification that's going on there. 4 and the 2 cancel, give it 2. 2 lambda is equal to 10, so lambda must be equal to 5 meters. You say, well, okay, well, that's something I can sort of sink my teeth into, because if I look at this, look, don't I kind of have like a wave here, and then there's another wave here, so there's 2 waves there, and 2 waves adding up to make 10 meters? Yeah, a wave is 5 meters long. And then I say, well, okay, this whole loop counting thing that we talk about, each loop, actually, if I count them up, I've got 4, but those 4 loops also lets me know that this is the 4th harmonic for a closed-ended air column. It's the 4th frequency at which resonance will occur, this 4th harmonic, the 4th frequency at which resonance will occur for this fixed-ended string. And so we had this equation Fn equals n times F1, where n is the harmonic number. Now the diagram here is the 4th harmonic, so n would be equal to 4. And if we knew, for example, that F1 was 3 hertz, so let's just say we knew that. The thing that was making this wave occur was vibrating 3 times per second. Then if somebody said, well, I would like to know what the 4th harmonic frequency would be, what's the 4th frequency at which this would resonate? So at the lowest frequency that the string would resonate is 3 hertz. Then what frequency is producing this particular standing wave up here? Well, just so as an aside, this is the diagram that would go along with that 1st harmonic. That is a diagram of the 1st harmonic's standing wave, the fundamental frequency, the lowest natural frequency of resonance, 3 hertz. But given this equation, Fn equals n times F1, and if we knew that that was F1, then F4, the 4th harmonic resonance frequency, would be 12 hertz, just following through that process. Now, if we brought this idea of wavelength being 5 meters and this idea of the 4th harmonic frequency being 12 hertz together, then we could calculate the speed of the wave that is on this string. Wavelength is 5 meters, frequency is 12 hertz. V equals lambda f, that's that universal wave equation from earlier. And so the speed of the wave traveling up and down this string must be 60 meters per second. So we're tying things together here. And we didn't stop at talking about resonance on strings, though. We also talked about finding resonance in air columns. And the first air column we looked at was open-ended air columns. Remember, with these open-ended air columns, there's no cap on either end of a hollow tube, and so the air is free to fluctuate in pressure at either end of that tube, and that's what these pink graphics are there for, is to represent fluctuation of air pressure. And so we would say that this is the 1st, 2nd, and 3rd harmonic. We would say that n is equal to 1, 2, and 3 for those 3 diagrams, because these n numbers are the harmonic numbers. We said that the length of a resonating open-ended air column has an equation n lambda over 2, where n is that harmonic number, lambda is the wavelength, and L is the length of the tube. In this case, I've labeled as 1 meter, right? So a little bit of figuring out that I want to do here before I carry on, though. If the 1st harmonic frequency was 3 hertz, Then the second one would be, now I'm just going to make a little note, remember that Fn is equal to n times F1. So the second harmonic, n is equal to 2. 2 times the first harmonic, 6 hertz. Again, for the third harmonic, 3 times the first harmonic, 3 times 3, because it's n times F1. 3 times F1 is 9 hertz. So we could calculate the harmonic frequencies for harmonics 1, 2, and 3. What if we wanted to find the wavelength? Remember, we have this equation. L is equal to n lambda over 2. Well, if I want to know what the wavelength is, I could rearrange this equation to get lambda is equal to 2 times L over n. In this case, the length of the tube is 1 meter, so 2 times 1 divided by 1. Okay, that one's just going to be equal to 2 meters. 2 times 1 divided by 1. Let's take a look at this one. Again, it's 2L over n. Great. This time, though, the n is equal to 2. So 2 times 1 meter divided by 2. Lambda 2 is equal to 1 meter. And then this one, 2 times L is still divided by n equals lambda, but this time n is equal to 3. So 2 times 1 meter divided by 3 is, I could say it's 2/3 of a meter, but sig figs, right? We could say it's 0.6 repeated meters, and we'd have to round it off to probably 0.7 because it looks like I've only given myself one significant figure. Bah, okay. Anyway, I could take each of those guys and I could figure out wavelength. Let's just talk about this briefly then. If I was trying to find the wave speed, v is equal to lambda f, just take our wavelengths then. 2 meters is the wavelength, 2 meters times 3 is the frequency, 2 times 3 is 6 meters per second. Let's just make sure, because this tube should have the same speed for its waves all the time. Let's just make sure that things are being consistent here. Again, v is equal to lambda f, 1 meter times 6 hertz. 6 meters per second. I want to make sure this is still true, though. 9, this is going to be hard. 9 times 2/3. 2/3 of 9. You guessed it, 6 meters per second. So this is consistent. The speed inside of this air column is 6 meters per second. Now, I want to go over and talk about closed-ended air columns for a minute. So I'm just going to come up over here and look at these closed-ended air columns. Reminder that we've got a first, third, and a fifth harmonic here. I want to remind you that there are only odd harmonics when we're talking about closed-ended air columns. So n is going to be equal to 1, 3, 5, and 7. But the same rules apply for harmonic frequencies. So I would say Fn is equal to n times F1 if I want to find out the frequency for these higher harmonic resonance frequencies. So if F1 was 2 hertz, then F3 would be 3 times F1, 6 hertz. And the fifth harmonic would be 5 times F1, 10 hertz. 5 times 2 is 10. 3 times 2 is 6. Okay, so harmonics n1, n equals 3, and n equals 5. And go back to the notes to get clarification on why we only have the odd harmonics. Now, just a quick little thing down below here. Remember, looking at lengths, L1 is equal to n times lambda over 4. So if I say n is equal to 1, that would be L equals 1 lambda over 4. Earlier I said that the length of this tube is also 1 meter, just to make things nice and easy. So lambda would be equal to L times 4 over 1. 1 times 4 divided by 1. This wavelength 1 is equal to 4 meters. I want to do the same thing for the other drawings. And I could say that it's still going to be L times 4, but this time the n value, remember this 1 was n equals 1. This time the n value is going to be equal to 3. So we'd say 1 meter, which is that L value, 1 times 4 divided by 3, that's, you do the math, 1 1/3, or I could say 4/3 of a meter, 1.3 repeated meters. And then the next one, we've got lambda 5 equals L times 4, again, over n. This time the n is going to be equal to 5. So 1 meter times 4 over 5. We'd say that the wavelength is equal to 4/5 of a meter, or we could say 0.8 meters. Now, if I wanted to go back and take each of these wavelengths and figure out what the speed is, again, same as we did with open-ended air columns, V is equal to lambda F. And if I apply that same equation, I'm only going to do it for the first one this time. You can check it with the other two if you want to. But V is equal to lambda F. If I have a wavelength of 4 meters, and from above, frequency 1 was equal to 2.0 hertz. That's just from my earlier diagram. And I'll just slide it up there to show you. F1 was equal to 2.0 hertz. So then I can say V is equal to lambda F. So that would be 2 times 4, 8 meters per second. And you check for yourself. This one here was F3 was equal to 6 hertz. And F5 was equal to 10 hertz. And you can confirm that 6 times 1.3 repeated is 8, and 0.8 times 10 is also 8, right? Again, consistent system of equations. And that's really helpful to recognize that these systems of equation are internally consistent. I want to go back over to this because this makes me think of a lab that we might have talked about. Resonance in air columns, where the air column changes length, but the frequency of the sound stays the same. So for this one, I want to say, let's just pretend we have a tuning fork that has a frequency of 1,000 hertz, and we find that there's resonance which occurs at the 2 centimeter mark. Cool. We hear it get louder when it's 2 centimeters long. This air column has been pulled up out of the water. It's been capped off at one end by water. It's a closed-ended air column, and we find that there's resonance at the 2 centimeter mark. Then you find resonance that happens at the 6 centimeter mark and at the 10 centimeter mark. Now, the only reason I've drawn the L2 and the L4 position is to point out that these diagrams represent no disturbance happening at the mouth of the air column, which really means that the even harmonics are physically meaningless. So we're just going to cross those out. I drew them there to show geometrically what they look like, but I'm pointing out that this is the physical reason for why we don't have even harmonics. So if we found resonance to happen at the 2 centimeter, 6 centimeter, and 10 centimeter mark, let's just go over to the side here and say, well, what if I found the difference in those resonance lengths? I want to point out the difference in length between the 5th harmonic and the 3rd harmonic. This distance, notice I'm just measuring over a difference in distance, is equal to lambda over 2. So L5 minus L3 happens to be 10 centimeters minus 6 centimeters, 4 centimeters. And that 4 centimeters is equal to lambda over 2. So lambda is equal to 8 centimeters. Let's make sure with the L3 minus L1. Again, L3 minus L1, if I draw the dotted line across, again, it would be lambda over 2. And 6 centimeters minus 2 centimeters, again, is 4 centimeters, equals lambda over 2. And so again, lambda ends up being equal to 8 centimeters. Now just converting over to SI units here, recall that we would maybe want to write lambda as 0.08 meters. But then also recall that the frequency was 1,000 hertz. So if I wanted to calculate what the speed of sound inside of that air column was, V is equal to lambda F. So 0.08 meters times a frequency of 1,000 hertz. What is that? 0.8 or 0.08 times 1,000 Oh, I'm so lazy. What am I doing? Is equal to 80 meters per second. Great, which actually isn't a realistic value, especially when you look at the temperature-dependent speed of sound, and you recognize that 332 meters per second is the speed of sound when it's 0 degrees Celsius. So, oh my gosh, this is ridiculous. This is definitely not a realistic value. If I got this value on an experiment, I have cause to question my results. But that's not what I want to pause for right now, to question that. But it would be, number sense wise, something that would make me pause, because there's no way that I'm doing my experiments in the classroom at a whole bunch of degrees below 0, which would be necessary for that to occur. All right. I want to go back and I want to look at one last thing, because it's something that I got a lot of questions about. Just a reminder, fixed-ended strings have this equation where the n values represent harmonic numbers. Open-ended air columns share the same equation. Also, for both fixed-ended strings and closed-ended air columns, we say F1 is equal to 1 times F1. F2 is equal to 2 times F1. F3 is equal to 3 times F1, where you notice that each of these coefficients corresponds to a harmonic number. And then for closed-ended air columns, we frequently use ln is equal to n lambda over 4, where these n values represent the harmonic numbers, and they're only allowed to be odd for closed-ended air columns. Remember, closed-ended air columns are physically those air columns that are capped off at one end, whether they're capped off by water or some other solid obstruction. They're not open at one end, so it's asymmetrical. And we end up saying that L1 is equal to lambda over 4, L3 is equal to 3 lambda over 4, L5 is equal to 5 lambda over 4, where again, these coefficients are harmonic numbers. Down here, we use the exact same equation, Fn is equal to n times F1, to figure out what the frequencies would be for the higher harmonic resonance frequencies. So third, fifth harmonic. Notice that they're always these odd harmonic numbers, never the evens. Here's the thing that people get upset about. And so I want to use the word danger, because there's this other equation, the other equation. Ln equals 2n minus 1, close bracket, lambda over 4. Again, this is something that gets used by some people in the world for closed-ended air columns. And so I present it in this course so that we can see it, so we can be aware of it. And this is the situation where we use n equals 1, 2, 3, 4 subbed into this equation. These are not the harmonic numbers. They're just integers. And I want to take a look at what happens here if we sub in these values. So if we use n is equal to 1, then what we end up getting is 2 times 1 is 2. 2 minus 1 times lambda over 4. And 2 minus 1 is 1, so 1 lambda over 4. If I do the next one, where n is equal to 2, 2 times 2 is 4. 4 minus 1 times lambda over 4 becomes 3 lambda over 4. And if I use n is equal to 3, then 2 times 3 is 6. 6 minus 1 lambda over 4 becomes 5 lambda over 4. And what you notice here is, put a circle around it, we end up having 1 lambda over 4, 3 lambda over 4, 5 lambda over 4. And you're like, wait a minute, why didn't these people just use ln equals n lambda over 4 and just remember that n's can only be odd? Because really, you're confusing yourself here, because these n values are not the harmonic numbers, and so you can't use these n values in this equation for calculating harmonic frequencies. So that drives some people a little bit crazy, and I just wanted to draw your attention to the problem. And that's actually why I tend to avoid this equation, just because it seems so much simpler to use this one and only use odd harmonic numbers for the closed-ended air column. So just to point out here that for this equation that we're talking about up here, the 2n minus 1 lambda over 4, when you use an n with this equation, the n equals 1 value would correspond to harmonic number 1. Yes, but the n equals 2 value would correspond to the third harmonic. The n equals 3 value would correspond to the fifth harmonic. 4 would go with the 7th harmonic, and 5 would go with the 9th harmonic. And this, more than anything, I think is not helpful for conceptual understanding. So I would just avoid that equation unless you really have a reason for passionately loving it. And I do have it on the equation sheet, just in case you happen to be one of those people that loves it. And that's all I have to say about sound.